Today we're going to talk about a very powerful trick for doing antiderivatives. This will allow you to do a lot of antiderivatives that are not just polynomials, which is basically what we know about so far. It's called the U substitution, or just substitution, but usually we use the letter U when we do it, so people call it the U substitution. Anyway, it's based on the chain rule. So we have the chain rule. Let me just write down the chain rule for the derivative. Says if you have something on the outside and another function on the inside, the derivative is the derivative on the outside with the same inside times the derivative on the inside, like that. All right. This is a rule about the derivative. It means automatically you get something about the antiderivative. If the derivative of this is that, that means the antiderivative of this is that. So the antiderivative f prime of g of x, g prime of x dx is equal to f of g of x plus c. All right? This is a true fact about the antiderivative. It's a little weird the way that this is written. This is the basis behind the U substitution method, although there's not much sense in memorizing this formula. You should think of the U substitution more like a process. But anyway, the way that we are typically going to think of this is you let U be g of x, and then du be this part here. So g of x is the thing inside of that, and then the rest, this I'm going to call du, g prime of x dx. And then if you write this rule, it looks a little simpler. I'm going to write this rule again using the u's and such. It says integral f prime of u, and then that's du equals this over here, but I'm going to write that with the u also, f of u plus c, right? If you have, if you have a sort of complicated thing like this, but you are able to figure out how to choose the u and the du appropriately, you can rewrite it this way, and then that you can find the antiderivative is pretty simple. All right, that's kind of the idea behind the U substitution. It's actually it seems kind of complicated at this level. I think it's best to just try to do a bunch of examples. The process involves looking at a fairly complicated thing inside of the integral and choosing the u and the du so that they fit this formula, and then you can do the antiderivative pretty easily. Let's just try some. Okay, here's an example of a fairly complicated thing inside of the integral sign. Now, in theory, you could actually do this by actually multiplying out the 6th power here. That would be pretty taxing to do, but you would do like the FOIL thing 6 times. You would never actually want to do that, but in theory it's possible. Instead, we can do this actually using the U substitution. The way that this works is you want to choose something to be U, and then based on what U is, you can determine what du is. And the way that formula worked, remember, maybe I'll remind us up here. Integral f prime g of x times g prime of x dx. This was the like complicated form of the integral that we saw, and we said I'm going to let u be the g of x and du be the g prime of x dx. Generally speaking, you want to choose the u to be the inside of some sort of more complicated formula, and I do see something on the inside here. I'm going to choose u to equal x squared plus 10. All right, not including the 6th power up there, just x squared plus 10. Okay, and then, so put that up here. What is the du? Well, according to the stuff that we just talked about, once you know what the u is, the du is always equal to g prime of x dx. So if this is g of x, the du is just the derivative of that. You take the derivative of that, so that's what the du is. And the answer is 2x. dx, you always include the dx as part of the du. Again, that was part of the formulation that we had before. I said this part is going to be the u, and this whole part is going to be the du. The du consists of the derivative of the u followed by dx, and that's what that is. All right. Anyway, having chosen the u and the du in this way, we're then going to plug everything into the formula here. So this is why it's called the substitution. I'm going to substitute wherever I see x squared plus 10, I'm going to put u. So that would be u to the 6. And then what is 2x dx? That's du. So it's u to the 6 times du. Awesome, right? I have done the substitution. Now you should kind of sit back and ask yourself, you still haven't done the integral, right? We still have the antiderivative sign there. But is this an easier integral to do now? Hopefully, after you do the substitution, the result at this step is simpler or somehow easier than what it was before. And is it? I think it is. This is actually quite a lot simpler. In fact, it's just a power of u, so you can now do the antiderivative. Now the variable is called u rather than x, but it doesn't matter. Use all your same tricks for doing antiderivative. So the antiderivative would be u to the 7 times 1 over 7. That's the power rule, plus c. And now the integral is done. One last step, because the original question was about find the antiderivative of this function of x, your answer should be written as a function of x. I don't want to see u in my answer. I want x's. That's easy though. This is always an easy step. You just replace the u by whatever its formula is in terms of x. So my final answer is 1/7 x squared plus 10 to the 7 plus c. That's the antiderivative. Need some new markers. So the first step of the U substitution is choosing the U. I got a new marker here. That look better? Looks better to me. Choosing the U. You got to look at that formula and somehow pick out a piece of that which you intend to be the U part. I did that last time without much fanfare. The general idea though, or the general strategy, is the U should be, I'll put this in quotes here, the inside of something or other. This is a vague guideline. Unfortunately, there is no real hard and fast rule about how exactly do you choose the U. You should choose the U to be the inside of something. Let's just do another example. You have to just kind of do a lot of examples to get a feel for how it goes with what you should choose the U to be. How about this? 3x squared square root of x cubed plus 1 dx. Okay. The first step will be to choose what part of this is supposed to be the U, and the general principle is the U should be the inside. The inside of what? I didn't say. The inside of something or other. In the previous example, the U was the inside of some parentheses. Here you don't see any parentheses, but there still is a thing which is worth, or which is kind of lends itself to being described as the inside. I am referring to the square root sign. So in this problem, I'm going to choose U to be x cubed plus 1. All right, you do not include the square root sign for reasons which you'll see. It works out this way to do it just like that. What's the du then? The du is always, remember, you take the derivative of the u, which in this case is 3x squared times dx. All right, and now you have to go over here and plug everything in. So this is equal to integral. Let's write this. What is well? How about this part first? All right, square root of x cubed plus 1. X cubed plus 1 is u, so this is just square root of u, all right? And then what's left over after having plugged that in, what remains in my formula is 3x squared and dx. Maybe I'll just put that over here as sort of an intermediate step. What are we going to do with this? You have to substitute in for u. All your variables inside of the integral need to be changed into u's rather than x's. So you're going to have to do something with this 3x squared dx. Is that equal to anything in terms of u? Well, yes it is. It equals du, in fact. So this actually is just equal to the square root of u du. Now it's not really necessary to write this intermediate step. If you can see what's going to happen here, the 3x squared and the dx is actually equal to the du, then you could have just skipped from here all the way down to here. Anyway, now we've done the whole substitution and it's time to actually do the integral. How do you integrate root u du? You write it as u to the 1/2 du, and then you do the power rule here. 1/2, you increase by 1, it becomes u to the 3/2. And then you divide by 3/2, which is the same as multiplying by 2/3. plus c. And the final step, as always, is to put the x's back in. So instead of u, I'm going to put x cubed plus 1. Just about out of room, I'll do it up here. My final answer is 2/3, so this equal sign comes from here, right? 2/3 times u to the 3/2, but that's u, so it's x cubed plus 1 to the 3/2 plus c. That's it. This is the U substitution. Now, the two examples I've done so far have been actually kind of easy. There's one more little intermediate step that sometimes you will have to do. Before we do that though, let me just remind us all that you can always check your answers with these on a test or something. It's a good idea to do this every time because you can always check your answer. Remember, this whole problem says the antiderivative of this is this. So you can check your answer in terms of the derivative. What that means, the antiderivative of this function is a function. That means actually, if you were to take the derivative here, you should get that as the answer. Let's try it. I'm going to start with this and take the derivative. Hopefully we're going to get that. Let's take the derivative of this. You're going to have to do the chain rule, right? Because I have a thing inside here and this thing also. The fact that 2/3 here is not a big deal. It'll just stay as a 2/3 in my answer. So it's going to be 2/3 times. All right, right here I'm doing the chain rule. The power comes down first. 3/2 times. Same thing on the inside. Decrease the power by 1, it becomes 1/2. And then the chain rule, I have to multiply by the derivative of the inside, which is 3x squared. All right? Take the derivative plus c, that becomes 0 because it's a constant. And we can simplify this a little bit. 2/3 times 3/2, they just cancel entirely. This to the 1/2 is really the same as square root x cubed plus 1, and then times 3x squared. And that actually is what we had before. It was written in the other order, but that is what appeared inside of the integral sign, so we must have done the antiderivative correctly. This is how you can check your answer on these, which you always can do, and if you have enough time on a test or whatever, you always should do it. All right, let's try another. Okay, let's try this one. It looks actually fairly similar to the one we just did. There's one extra step which is necessary here. The extra step is divide by a constant to make the du match. Did you hear that? Divide by a constant to make the du match. I'm going to write that in voids. Divide by a constant to make the du match. I don't know if that means anything to you at this point. It will mean something to you when this comes up. It's going to be an issue in this case. Anyway, let's begin. As always, you should begin by trying to choose something to be the u. I suggest the inside of something, that is the inside of some parentheses or the inside of a square root sign. I think it's obvious here. The inside of these parentheses would be x squared minus 1. You do not include the exponent also, only the inside. All right. What is the du? You take the derivative of this, 2x, always followed by dx. The du always includes the dx. Okay? So let's try and plug everything in here. I'm going to do it just like I did in the previous problem. First of all, the inside of the parentheses is u. So we have u to the 2 over 7, right? That's this part right here. And then what's left over is x times dx. So I'll just sort of gather those guys over here. U to the 2 over 7 times x dx. Now, we have to plug something in for the x times dx in terms of u. The problem, and this did not happen in the previous examples, the problem here is du is equal to 2x dx, but I have x dx here. What's a fella to do? It says 2x dx, even though what I have over here is just plain x dx. What should I do? Do what I told you over there. Divide by a constant to make the du match. What I mean is right here, I'm going to divide both sides by 2. 1/2 du equals x dx. What do you think of that? Why did I do that? Because now it does match. X dx is 1/2 du. So this is integral u to the 2 over 7 times 1/2 du. How you like that? Now I have replaced all the x's by u's, and so we can proceed to do the antiderivative. Let's do the antiderivative now. As a preliminary thing, and you should always do this at this step, let's pull the 1/2 out because it's a constant on the inside of the integral. So 1/2 integral u to the 2 over 7 du. And now you just do the power rule here. You increase the power by 1. So the 1/2 stays in front of your answer. Now we increase the power by 1. 2 over 7 plus 1. 1 is 7 over 7, so this is 9 over 7. Then we divide by the new power, so that's dividing by 9 over 7 is the same as multiplying by 7 over 9. And then plus c. That's about it. Last step, as always, put the x's back in for u. And it ends up being 7 over 18. I just multiplied the fractions. And now u is x squared minus 1 to the 9 over 7 plus c. There you go. Divide by a constant. Typically, you will have to do this step. Usually, it's kind of magical if this matches exactly the du. Usually, that doesn't happen. Usually, you have to introduce a new little 1/2 or something like that to make it actually match up. But this is the way it goes. I got 3 more examples to try. All right, let's do this integral, x over x squared plus 1. Now, I said before, how do you choose the u? The u should be the inside of something. It doesn't really look like there's anything that would count as being the inside of something or other. You have to expand your definition of inside a little bit. There is a fraction here. It turns out oftentimes choosing the inside of the denominator is going to be a good idea. So let's try that. The inside of a denominator. The inside of the denominator. So that would be u equals x squared plus 1. Let's see what happens. What is the du then? You do the derivative, 2x, and then dx. Okay, let's try and plug in here. I got integral here. I'm not sure about the x, but the down there is u, right? So this is x over u du, right? Let's kind of, I like to kind of separate out the parts which already have the u's in it and the parts which are kind of left over. Not du, sorry, that should be a dx. I don't have du in there just yet. Dx. Okay, so this is what I mean by separate out. 1 over u times x dx, right? That's the same as that. I did that just because I have this is already dealt with. We don't have to worry about it anymore. This, though, needs to turn into u's somehow. And this, hopefully, is going to match with the du. It doesn't match exactly because of that 2, but what do we do in that situation? We divide the constant. So you divide this 2 across. It says 1/2 du equals x times dx. And that's what we can plug in here. So I get integral 1 over u times 1/2 du. Now the substitution is done. Everything is in terms of u, and we can try to do the integral. As usual, pull the constant out. 1/2 integral 1 over u du. And what is the integral of 1 over u? Remember the formula for integral 1 over x? It is natural log of absolute value of u. So that right there is the integral. The 1/2 just stays in the front. Last step, as always, plug the x's back in. So 1/2 natural log absolute value x squared plus 1 plus c. That's that. Another one. How about integral x squared times 3 to the 4x cubed plus 7 dx. What do you think of that? I got an exponential function. Anyway, what should we choose to be the u? Choose the inside of something. In this case, you should choose the inside of the exponent. This is a weird thing up there. Let's choose that to be the u. So it's going to be 4x cubed plus 7, right? What is the du? It is 12x squared dx. Okay. At this point, if you're getting used to doing this process, you'll begin even right now. Look back here and see. Do you see this 12x squared dx as any part of this? Actually, you should feel pretty good about this because you do see x squared here and dx here. Just to make it match, as we usually do, I'm going to divide the constant. 1/12 du equals x squared dx. All right, that's going to help us out in the next step. Anyway, let's try to do the substitution. We have x squared and dx. I'm going to put that together over here. X squared and dx, right? What is this? 3 to all of that stuff? Well, all of that stuff is u. So this is 3 to the u times x squared dx. And what's x squared dx? It is 1/12 du. And we did the substitution. How do you like that? All right, let's finish the integral then. Pull out the 1/12. 1 over 12 integral 3 to the u du. And now you do this integral, you got to remember your formula. The formula is integral a to the x dx is 1 over ln of a to the x plus c. Remember that thing? So that's what we're going to do here. The a is 3, and instead of x, it's called u, but that doesn't matter. So it's 1/12 times 1 over natural log of 3 to the u du. All right? And as always, the last step is to put the x's back in instead of the u. So my final answer is 1 over 12 ln of 3 to the power 4x cubed plus 7 plus c. I put du there. What was that all about? That's not right. That ain't right. Should have been a plus c. Sorry about that. All right. There you go. Let's try one last example. All right, this is a pretty weird example. This is meant to demonstrate the fact that sometimes you got to break all the rules when you're doing the U substitution. If you just have no other options, sometimes you just got to try something that is not really the inside of something. You got to try whatever works. This one here, there is no real inside of anything. You could try to choose the denominator as the u, but it turns out that wouldn't work. Actually, let's see what would happen if you did that. You go u equal x, that means du equal dx. So that is u, and that's du. So this is ln of x over u times du. What are you going to do with this x here, this ln of x? Is there any way to turn that into u's? If you ever find yourself halfway through the substitution and then you don't know how to change part of it into u's, that means you probably chose the wrong value for u. The best you could possibly do would be, well, u is equal to x, so you could actually put u up there. ln of u over u du, right? Now, so the substitution is over. You should step back and ask yourself, do I know how to do this one now? You know, usually after the substitution, it's something you know how to do. Do I know how to do this one? Is it any better than what we started with? No. In fact, it is exactly the same as what we started with. The only thing you did was change the name of the variable from x to u, all right? This is a useless substitution. In fact, u equal x is always a useless substitution. You'll always just get the same thing again. So never do u equals x. It's not wrong. It's useless. It doesn't get you anywhere. Let's try a better idea. A better idea, really, the only other idea that you would ever think of would, I guess, x didn't work. Let's try ln of x for the u. All right? Well, okay. You shouldn't be too optimistic about this, but it turns out actually this is going to work in this case. What is du? You do the derivative of ln, and you get 1 over x. dx, the du always includes the dx. All right, let's go back here, plug some stuff in. What do we get? The ln x here becomes a u, and I'm going to, as I have done in the past, I'm going to split this apart, gather all the stuff with the u's to the left, and then leave the stuff with the x's to the right. It's going to be u times 1 over x dx, like so. All right? What do you do with 1 over x dx? Hey, that actually is equal to du, so the answer is integral of u du. What do you think of that? Can we do this one? You bet you can do this one. This is like u to the 1 power, so you just do the power rule. You go 1/2 u squared plus c, and then as always, put the x's back in. 1/2 natural log of x squared plus c. That's that.